Hi everyone. Today I want to continue chapter 13. In our previous class, we talked about how we can find the equivalent model for different elements in the circuit. Now today I want to do a quick review and then I'll solve some example to show you how we can solve circuit in Laplace domain. So we are talking about chapter 13, which is about Laplace transform and circuit analysis in Laplace domain. Okay. First, let me review what we discussed in previous class. In previous class, I showed you how you can model an inductor and a capacitor in Laplace domain. So if you have an inductor, let's assume that the initial current, I use another color. Okay, let's assume that the initial current is I naught. I want to see how I can model this in Laplace domain. So in order to model this in Laplace domain, I can use either series circuit or parallel circuit. If I'm using series equivalent circuit, then I have to use a voltage source, and just to remember which direction I have to choose for the voltage, the source should produce the current that is in the same direction as my initial current. So this is going to be the polarity. So here I have LS, and the value of the voltage, I showed you the proof that that's equal to L I naught. And if I'm using the equivalent parallel circuit, then I have to go with LS here, and then here I have to model the current. So it's going to be a current source with a current direction in the same direction as my initial current, and the value of the current source is going to be I naught over S. So this is the equivalent circuit for an inductor. Now let's see how we can do it for capacitor. So if we have a capacitor, and this is an inductor. Okay, let me delete it. If we have a capacitor, and this capacitor has a value of capacitance equal to C, and its voltage is equal to its initial voltage is equal to V naught. Let's see what is going to be the equivalent circuit. Again, I can model this in either series circuit or parallel circuit. In both of them, the impedance of the capacitor is equal to 1 over CS. If I'm using the series equivalent circuit, then the voltage should have the exact same polarity. So it's going to be plus, minus. And the value of the source is going to be V naught over S. And if I'm using the current source, then the current source should be in a way that it basically comes out of this voltage here. So now this is my voltage, and the value of the voltage source is going to be C V naught. So these are two equivalent circuits that you have to use for your inductor or capacitor if you are planning to solve your circuit in Laplace domain. They help you to consider the initial values of your elements. So let's say I have an RC circuit and I want to find the natural response using the Laplace transform analysis. So I'm going to draw the circuit here. So this is an RC circuit, and this capacitor is going to be connected to a resistor by a switch, and the switch will be closed at t equal to 0. Now remember that this capacitor has an initial voltage equal to V0, and the switch is going to be closed. The question is that what is the natural response? So we are looking for something is wrong. Natural response of this circuit. So in order to solve the circuit, here I have C and here I have R. In order to solve, what I have to do is that I have to model my capacitor by one of these two equivalent circuits. Let's go with the first one. So I'm going to solve it with the first one. Honestly, in this circuit, it really doesn't matter which one you are choosing. But if you have a more complicated circuit, it's better to choose the one that makes the solution easier. So if the neighboring elements are all in series, it's better to go with the series one. And if all of them or most of them are in parallel, so it's better to go with the parallel one. Let's see how I can solve this one. So I'm going to go with this model. So let's use black for the solution. So I have a voltage source, which is supposed to show me the effect of the initial voltage. And then after 0, the circuit is connected to this resistor. So the source is going to be in the same polarity of similar to my initial voltage, and the voltage value is going to be equal to V0 over S. So V0 over S. And this capacitor is going to be 1 over CS. And here I have my resistance. So now if I'm looking for the current in the circuit, let's assume that my initial circuit, I was looking for I of t and for V of t, in which I is here and V is the voltage here. Now, this is my equivalent circuit in Laplace domain. So what I have here is Laplace domain circuit. Now, in my Laplace domain circuit, okay, let me delete something here so it makes it easier because I want to keep my circuit here. Okay, so in this circuit, what I have to do in order to solve the circuit is a very simple loop, and it tells me that I in this circuit is equal to V0 over S divided by all the impedance in front of it. So R plus 1 over CS. So now what I'm going to do is that I'm going to multiply this fraction by S over R, so both numerator and denominator. Why? Because I have to get rid of this S in denominator, and also I want to get rid of the coefficient of S that appears here. So if you multiply both your numerator and denominator by S over R, what you're going to have is equal to I as V0 over R divided by S plus 1 over RC. Now this is my Laplace domain solution. And if you want to have your time domain answer, you have to do Laplace inverse here. So this is a very simple fraction that I can easily do the Laplace inverse. If the fraction it has higher order, then what you have to do is that first you have to apply PFE to get partial fractions, and then you can apply Laplace inverse. But here I have a very simple partial fraction. I don't need to apply any PFE. So the Laplace inverse is going to be it's better to go with I of t actually. So I of t, because I'm talking about time domain. So I of t is going to be V naught over R, that's the coefficient. And then I'm going to have e to the power of minus t over RC. So if you remember, that's the exact same thing that you had in 211 as natural response of an RC circuit, but you were solving the circuit in time domain, and it was more complicated because you had to deal with differential equation and you had to solve differential equation. Here, everything is algebraic equation, and then at the end we have a Laplace inverse. So that's the natural response, what we have for the natural response of an RC circuit.